All right, in this video, I'm going to show you how to make an ignition extinction curve. So basically, an ignition extinction curve is a plot used for a CSTR. It's going to tell us if we're operating at this region down here on our GFT plot. So in this case, we aren't operating down there because, of course, where we're operating would be where the point of intersection between our RFT plot and our GFT plot is. So let's pretend that we are operating down there. So if I change my feed temperature, for example, so now I'm operating down here. So if I'm operating in this range and I'm gradually increasing the feed temperature, to what temperature would I have to increase it to operate up here? And we looked at this in the last example. We know how to find that. So that's going to give me the ignition temperature. And the same as if I were operating up here. So I can go back to the high feed temperature and I start operating up here. If I gradually turn down the feed, what would happen to the reaction temperature? And when would I go back to operating down here? And the reason that's important, here I'm getting essentially no conversion, and here I'm getting a conversion near 1. So I want to know when or what temperatures, if I'm gradually changing my reactor feed temperature, which is gradually changing the temperature of the contents of the reactants, at what temperature do I jump from a low conversion to a high conversion, and what temperature do I jump from a high conversion to a low conversion? And that's important to know both because I want to be operating at high conversion, but also because if I'm operating at a low conversion and then I jump to a high conversion, all of a sudden I'm going to have a lot more heat being generated in the reaction. So I'm going to need to hope that my cooling system can quickly account for that, right? So a cooling system that has been operating for a low conversion, can it, if I change my feed temperature by 1 degree and that causes my reactor temperature to jump significantly, can my cooling system respond to be able to handle that? So it's good to know where this happens, these temperatures that this happens. And one way that we do that is to plot what's called an ignition extinction curve, which gives you the reactor temperature as a function of the feed temperature. So that's what I'm going to do here. So basically I've copied this worksheet into a new worksheet. I've made it a little bit smaller because I want to include more information on it. And here I have an already solved example, but I'm going to walk you through how I do this. So basically here is my GFT and RFT curve. And we said in the last lecture that I can basically shift this RFT curve to the right or the left basically by changing this feed temperature. So right here I'm at 338. I can start as low as 300 and I can go up to as high as 500. And when I do that, I get various different intersections between the red curve, S curve, and the green curve, straight line. Those are all different steady state solutions to my CSTR energy balance. So what I want to do here is change the feed temperature and see how the reactor temperature changes accordingly. So I'm going to start down here at 300. And so what I've done here is I've made an energy balance solution. It depends on this feed temperature. And then I have said I've made a guess for what my reactor temperature will be based on my feed temperature. And from that, I've solved for K, the rate constant, and XMB, the conversion due to the mole balance. And for the for the solution, what I need is for the energy balance and the mole balance, or in this case, it would be actually the RFT and GFT plots I need for those to intersect. So that means that the difference between RFT and GFT should be equal to 0. So I've made a cell here where that is equal to 0, and what I'm going to do is use the Microsoft Excel goal-seek function to set this difference equal to 0 by changing this cell, which is the reactor temperature. That's going to give me the reactor temperature that satisfies that condition that GFT and RFT are equal at this particular feed temperature. So I do that, I get a value just over 300, and in fact if I look at my plot, that's what I would expect because that's about where those 2 points are intersecting. And so what I'm going to do here is copy this value, and I'm going to paste it here, and I'm going to say paste special, and I'm going to say values. So that's going to give me, for a feed temperature of 300, I found that my reactor temperature is also essentially equal to 300. And that's what I've done here. So I've done that at 300, 325, 350, 375, 400. The next one I tried was 425, actually. So I went to 425 here. But when I do that, I, of course, miss my ignition temperature. So what I want to do on an ignition extinction curve is I want to see the temperature where the conversion and hence the temperature of the reactor increases. So I already knew what that was because we solved this in the last problem, but if I didn't, I can learn that by changing this value and trying to get closer to where we see the green line making a tangent to the red line. And so I find that at 404 degrees Kelvin, I get a good tangent line here. So what I'm going to do here is I'm going to make this goal-seek solution. And I see I get a temperature of 340.74. And in fact, that's what I get here. So now if I were to go one more degree up, so what I want to do is find my ignition temperature and then go one more degree forward. So I go to 405. Once I go to 405, if you look at this graph, if we were to zoom in here, the green line is no longer touching the red line. So I would expect that my next point of intersection would be this one up here. And in fact, if I run the goal-seek function here, see, it takes a little bit longer because it wants to find a solution around this range of 340, but it can't. So it hops up to 384. And so I put that value here. So I copied and pasted that value here. Again, when I copy and paste it, I'm using copy and then I go paste special and values, and that takes the value from the cell and places it there without any cell references. And so beyond that, I can just keep going. So now I could go back to adding 25 increments of 25, and when I do that, I see my lines shift and my solutions shift. For my ignition curve, I don't need to do that, so I've already captured what I want to capture. So this is my ignition curve here. Basically, what I want to say is I want to plot T naught versus T combinations. So T naught on the x-axis and T on the y-axis. T naught is the feed temperature and T is the reactor temperature. I want to plot, or I want to capture this region where T versus T naught is relatively linear. And then I want to capture my ignition temperature. And then I want to go, once I have my ignition temperature, I want to go 1 degree hotter. That's going to give me this jump. So this is the point I need to illustrate on my ignition curve, is this right here. So this, if I change the temperature to 405 degrees, all of a sudden I'm now operating at the upper steady states. So I can do the same thing for my extinction curve. So my extinction curve is going to tell me if I'm operating at this high steady state, what temperature, what feed temperature, and I'm changing the feed temperature gradually, what feed temperature would I need to decrease to in order to start operating at the low steady states? So to do that, I started out at a somewhat high temperature. I started at 495. We see there we get a pretty high reactor temperature, about 410. And in fact, if we solve for that, it's actually 415. And then I backed it down, 470, 455, 430, just picking numbers kind of, because if I'm just moving along here in this linear range, I don't have to be so detailed in my analysis. So I'm just kind of, picking numbers along this range to give me a reasonable number of points, but I don't need to go 1 degree by in every step here because I'm basically just getting something linear. And you see this is plotted here. And I do this until I get down close to my extinction temperature. And so we know what that extinction temperature is, but let's walk down a lot more. So we went from 405, and these again are just temperatures I picked, 380, and then the next one that I picked maybe is 355. Let me see 355. Now I look at my RFT curve, and I'm no longer operating at any of these upper steady states. So if I wanted to find or identify my extinction temperature, I would need to find the place where this green curve and this red curve are tangent. And we looked before in the last video, and I think we said that was 362. I actually found in this video that it wasn't 362, it's 364. I don't know what happened there. Okay. So in the way that I found that was, so I put 362 here, and I use my goal seek function. And I'm telling a guess of 384 Kelvin, which means, if there is a solution near 384, it should find it. But what I find out is that after a lot of iterations, it goes down to 320. So that tells me, okay, there probably isn't a solution for this feed temperature on the upper steady states. So I increase by one more and do the same thing. In fact, I'm going to start higher again. I do that, and I get another low temperature. So, okay, let's try again. And when I go to 364, I find a solution, and that gives me a temperature of 365 in the reactor. So that tells me that my extinction temperature is actually 364. That's the last place where I have a solution at the upper steady state. So if I go here, that's what this combination of values is here. For a feed temperature of 364 Kelvin, the reactor operates at 365.5. This 364 Kelvin is my extinction temperature. So now I go just 1 degree below that, and that's going to give me my extinction curve. So I say 363 for my feed, and then I can solve for the temperature that meets, and we're going to see, as we saw a minute ago, that goes down to the lower steady states. The temperature drops, and my point of intersection is down here at 321.2. So that value is how I got that. And then I can continue subtracting the temperature if I want to. I don't need to. But basically, my extinction curve then is this one. I start at a high temperature, and I go down to 1 degree below the extinction temperature, and I get a curve like this. So this is my extinction temperature, and then 1 degree below it takes me back down to my lower steady states. So this part of the curve, the ignition temperature, that's important because we want to know at what temperature, if I'm operating in a low steady state and I'm gradually adjusting the feed temperature in order to adjust the reactor temperature, the hotter I make that feed temperature, the hotter the reactor temperature is going to be. At what temperature am I going to cause the reactor temperature to jump significantly? And the reason for that is I need to make sure that my cooling system is prepared to handle that. So most cooling systems are not going to respond immediately to that change. And the problem there is that it's a chemical reaction. So it's reacting away, it's reacting away, it's reacting away. If the heat generated curve let me rephrase that. If the heat removed curve cannot compensate or can't catch up with the heat generated curve, then we're going to have a scenario of reaction runaway. So it's good to know what the temperature is so that, we can, if we're adjusting the feed temperature, trying to get up to this range, we can ahead of time adjust the cooling temperature or the cooling system so that it's ready for that jump to happen. The reason I'm interested in this curve, the extinction curve, is because I really don't want to operate at this lower level. That is where I'm getting near zero conversion. So I really don't want to operate my reactor where I'm achieving 0% conversion, because then I'm not producing any products. So if I'm adjusting my feed temperature in order to control my reactor temperature, I want to know what temperature I would have to decrease it to in order to fall off of this high conversion. So now I think the question that comes into play now is, okay, first of all, why is this ignition temperature higher than the extinction temperature? Why aren't they the same thing? So the reason for that is because a CSTR operates at multiple steady states. So, for example, if I took my temperature here and I just changed it slightly to 370, we see now that this green line is intersecting this red S-curve at 3 different points, one here, and one here. So all of those are steady state solutions to the CSTR under this set of conditions. So the CSTR could be operating at any of these points. And the one that it's going to be operating at is the one that's closest to the conditions when the new set of conditions came into play. So if we were operating down here, and then for example, at a feed temperature of 340 Kelvin, and then we increase the feed to 370 Kelvin, we would operate here. So our reactor temperature would go up until it found the next available steady state, which would be this one. So, and if we increase it again, 380, the reactor, so I increase the feed temperature, that heats up the reactor contents until it finds the next steady state solution, which would be this one. Also, if I'm operating up here, so if I'm operating at a feed temperature of 450 degrees and I decrease that, so say I decrease that to 430. When I do that, I'm adding less heat to the reactor because the feed is cooler. Because of that, the reactor contents are going to cool off, but they're going to cool off until they find the next steady state, and they're going to operate there. So that's another reason it's important to know the ignition and extinction temperatures. So for example, if I'm operating at 404 degrees Kelvin right here, and I increase the temperature by 1 degree, now this is the reactor temperature is going to heat up, and the next place that it finds a steady state solution is all the way up here. So the temperature is going to increase dramatically. So you can see that when I'm operating on this line or this line, I can change the feed temperature, and because the place where I was originally operating is very close to the next solution, I have a minor influence on my reaction temperature. If I operate near the ignition or extinction temperature, I have a more major influence. Regardless of what's going on, there's multiple steady states in this system, and the one that the reactor is going to operate at is the one that's closest to the one where it was previously operating. So if I make a change, you're basically going to follow this line one way or the other until it finds the next available steady state. So that's basically what I wanted to say here. Basically, the CSTR curve, and there's regions of this curve where there's different operating conditions where we can be operating at multiple steady states. The one that the CSTR will operate at is the one that's closest to where we initially were. The one issue here that we need to be important of is where the reaction will light off, and then also where it will start to die off, the feed temperatures that will do that. We need to know these things, so when we're starting up a reactor, we're probably going to start at a low conversion, and we want to know the temperature to be able to gradually heat the feed to in order to be able to operate at the higher steady states. But we also want to be prepared to make sure our cooling system is already ahead of time operating at this level so that we don't get into a situation of reaction runaway. Also, if we wanted to cool our reaction down or shut our reactor off, one way to do that would be, if we're operating at an upper steady state, would be to gradually turn off the feed until we get back down to zero conversion. And we can know what the temperatures to do that are by plotting an ignition-extinction curve, which is basically, if I specify a feed temperature, what is the reactor temperature that will result if I am thinking about gradually increasing or gradually decreasing. So you see in this plot, there are values along these these trends where the CSTR has multiple steady states, but we are always taking the one closest since we're thinking about gradually turning up the temperature. So for example, going from 380 to 390. In both cases, there's 3 possible steady states. If we were previously operating at a lower steady state, then we will just move the temperature up a little bit. If we were operating at an upper steady state, then we would just move the temperature down a little bit. And rarely are we ever operating in this region because these are unstable steady states.